In the evolving landscape of automated driving, the transition of the driving task from humans to automated system necessitates a redefinition of the human role. In SAE Level 3 or Conditional Automated Driving, drivers are relieved from the driving task but must remain ready to take over when requested. The challenge is to keep the drivers engaged and prepared, also referred as fallback ready, as the driver is the fallback of the automation. In this paper, an eye-gaze heatmap analysis of uncertainty head-up display designs for conditional automated driving, we evaluate HUD design interventions that keep fallback-ready drivers in the loop while engaged in non-driving related activities to improve safety and usability. In this presentation, I will use the acronym NDRA for the non-driving related activity, a task fallback-ready drivers might engage when the automation is active. All treatments, including the baseline, have a display projected on the road ahead. That shows the NDRA, in our case an entertainment screen showing videos. The first intervention shows bars that visualize the uncertainty of the automation on the immediate side of the screen. These indicate how confident the automated driving system currently is. If the bars are smaller and green, the situation is less complex and confident with driving. If the bars become bigger and red, the situation is more complex and there's a higher likelihood that the vehicle reaches a limitation. The second intervention will hide the display when the situation gets more complex and ask the fallback-ready user to check the environment to make themselves aware of the situation. This notification is not a request to continue driving, but the likelihood is high that the system might reach a limitation. The third intervention combines both bars on the side to indicate the uncertainty of the automation, and the system hides the display when the situation gets more complex and asks the fallback to check the environment. The treatments are therefore organized by a 2x2 design, with the uncertainty display in the one dimension and the managed interruptions in the other. We conducted a between-subject designed driving simulator study with 215 participants in our advanced driving simulator at CARS-Q and QUT. The participants were primarily recruited over social media and distributed equally in age and gender over all 4 treatment groups. To simulate automated driving, a drive was pre-recorded and played back in our Wizard of Oz design setup, which we have published before. You can find more details about the method here. In this work, we are focusing primarily on the eye-tracking data of the entire drive, but will mention all measures that have taken to provide details about the participant context. The visit of a participant started with an onboarding phase, including the setup of the biometric sensors. We then seated the participants in the driving simulator where they have experienced an extensive familiarization process, including a safety briefing, an introduction of the study, a common understanding of conditional automated driving with its limitation, and a demonstration of the request to intervene. Lastly, in the training drive, we gradually introduced an NDRA and an explanation of the interventions and concluded in an extensive familiarization drive of the complete study setup. Once familiarized, participants did their data collection drive on a different route which started in the city area, continued with a long highway drive, and ended in a suburban area where the hazardous driving situation emerged. After the drive, participants filled out several surveys: the Situation Awareness Rating Technique, Unweighted NASA TLX, Trust in Automation, System Usability Scale, and a Motion Sickness Questionnaire. In the end, they were further debriefed in a semi-structured, open-ended interview. Now, let's look into the results. It should be noted, of the 215 participants, 209 eye-tracking recordings were valid. As the entry point of the data analysis, we looked into the percentages of participants per treatment group that have gazed in the NDRA over the entire drive. On the x-axis is the time of the collected drive. As reference, you see the top of the driving areas: city, highway, and suburban. On the right y-axis in red, you see the value of the uncertainty over time and the threshold that triggered the interruptions in the interruption conditions. On the left y-axis, you see the smooth overall percentage of the eye gazes of treatment group that has gazed towards the NDRA in percent. When we now compare the treatment groups with the baseline, which is marked in blue, we can observe that the engagement towards the NDRA has increased with the uncertainty display, while the engagement in the NDRA has decreased for both interruption groups. To verify this finding, we conducted a one-way between-group ANOVA combined with a group-wise comparison. Results show there is a significant difference between interruption versus no interruption. This was expected and makes intuitive sense because we effectively take the video display away in the interruption groups. So we looked further in the data and removed the moments where the NDRA was not interrupted and found even if the NDRA was not interrupted, participants in the interruption group gazed significantly less in the NDRA, presumably to monitor the driving environment. Lastly, we have created heatmap videos of the driving videos and coded them into identified events. Given the short time of this presentation, we present just one important finding. More details can be found in the publication, and we also publish the entire heatmap video in the appendix and can be requested in better quality. Both interruption groups created a unique eye movement pattern, which we compare with the flame of a candle. Drivers in these groups repeatedly looked back at the road in a rhythmic way, especially after entering the highway where interruptions were less frequent. This echo effect was observed strongest in the group with the combined interruptions and uncertainty display T3. What does this change mean? Drivers in both interruption groups T2 and T3 displayed a consistent pattern of checking the road even during uninterrupted stretches, suggesting an increased awareness of their responsibility as fallback. The interruptions might have nudged drivers towards becoming passive observers, requiring less mental effort to switch between the display and the driving scene. This behavior aligns with the concept of task interleaving, where users frequently switch their attention between tasks. Our study demonstrates that this can occur without a complete transfer of control and without sacrificing user experience, which can be read in the publication. However, further research is needed to understand the long-term impact of these echoes on the factors like drivers' ability to retake control, mental workload, and the potential compliancy towards the automated system. Our work demonstrates the approach of an interruption management system while using the NDRA as a carrot on a stick with the aim to maintain situation awareness in conditional automated driving. This work identifies new gaps in research you might like to build on. Please check the paper for more detail. The study is the first publication of this large-size data collection, and we will continue investigating the data in more detail. If you're interested in this topic, please reach out to us. We are open to collaborate and happy to discuss and share ideas and data. Thank you for your attention. Now I'm happy to go with you in discussion and open for questions.